Thanks to all the organizers for inviting me here. I'll be talking to you about memory of initial states in quantum dynamics, and I will focus on a particular problem, which is density imbalance in disordered interacting systems. I'll tell you what this is as we go along and how we keep track of memory of initial states in quantum dynamics. Okay, so since this is on thermalization, MBL, and hydrodynamics, well, most of you know all these things about many-body localization, but let me just set the stage. So the strongly disordered systems behave qualitatively differently from typical many-body systems that we learn about in StatMech textbooks. Okay, there's absence of transport even at finite temperature. There's an inability of the system to act as its own heat bath. If you look at the level statistics of the eigenstates, it gives you some Poissonian level statistics, and then the eigenstates have short-range entanglement. These are various, there are many other characteristics, but these are some of the most important characteristics of a system which is many-body localized. Okay. Now, all of this will actually be true even in a non-interacting system, and then you will call it Anderson localization, which is of course a very old problem. And then of course, if you have interaction and these properties survive, you would call this a many-body localized system. And there's a bunch of work, you have seen some of the lectures here, and it's one of the states where you can't really apply equilibrium statistical mechanics, okay? So why am I talking about MBL when I told you I will talk about memory of initial states? And the answer comes from, so if you look at systems where equilibrium statistical mechanics holds, the idea is that many-body systems forget their initial conditions at long times, at least if they're starting from some typical states. And what we mean by that is that if you look at local observables, their expectation values are determined from an ensemble which is defined only by the Hamiltonian and has nothing to do with the initial state I prepared the system in, and other kinds of quantities if they're there. Okay? Of course, you can make more precise statement for quantum systems in terms of eigenstate thermalization hypothesis. We have had a few talks here talking about eigenstate thermalization hypothesis. So I'll not go and talk about it in quite some details. Many-body localized systems, on the other hand, retain memory of initial states at long times, okay? So the local observables that you can think of, many of them would depend on where I prepared the state, what were their values in the initial state, and so on. And although they are not conserved, of course, for conserved quantities, this is a obvious statement, but the idea is even if you take quantities which are not conserved, their values at long times depend on the initial values. And this leads to the idea that there's a lack of thermalization, that if your system knows about its initial conditions, you could not have had equilibrium statistical mechanics applied to this system. Okay. Now, the nice thing about the second slide versus the first slide is, the first slide is things that you can see in numerical experiments, but in real experiments, you cannot really go and look at the Poissonian statistics or the entanglement entropy or so on. However, this fact that the many-body localized systems retain memory of initial states at long times, this can be seen in experiments. So let me go through the experiments that have been done. First, I will give you a theorist cartoon of what the experiments are doing, and then we will get to the actual experiments. So the idea is you initialize the system in a Fock state, let's say in real space. Let's say I have a lattice system, and I basically initialize in a Fock state where there are one particle on a set of lattice points, let's call them set A, and let's say the rest of the lattice points A bar have 0 particles, okay? So if I look at the density at initial times, it's 1 if the site is part of this set A, and it's 0 if it is part of the set A bar, okay? So this is the general setting, and then you let the system evolve. It's a closed system, you let it evolve under its Hamiltonian, and then you go and measure the density imbalance between the A and A bar sites, okay? So you calculate something which looks like sigma I ni of t, sigma is 1 if I is element of A, sigma I is -1 if I is element of A bar. So it just looks at the density imbalance between the A and A bar sites, and then you normalize it by the total number, okay? And this is what you would call imbalance. Now, if your system thermalizes, the Hamiltonian is such that it does not distinguish between A and A bar sites. The imbalance in a thermal state should be 0. And if you see that there's a finite imbalance in the long time limit, this can only be coming from the memory of the initial states, and this is taken as an indicator of lack of thermalization. This is often taken as a signature of MBL in these experiments. You can quibble about whether this is a true signature of MBL or not, but this is what people look at when they look at memory retention in these strongly disordered systems, okay? So here is the experiment. This has been flashed in a talk earlier in the conference, but let me just go through it. So instead of a disordered model, you look at something which has an incommensurate potential. So it's a cosine potential with an alpha, which is square root 5 minus 1 by 2. This model was, the non-interacting version of this model was written down by Aubry and Andre in 1980s. And what this allows you to do, just the non-interacting part, is that it allows you to change the V here and go through a localization, delocalization transition in one dimension. If you take the random disordered Anderson model, it doesn't have a localization, delocalization transition in one dimension. Okay, and it turns out that there is a localization, delocalization transition exactly at V over J equal to 1, again in a non-interacting model. So now you take this model, you build it in a cold atom-like system, and then initialize this cold atom system into this state, which is 1, 0, 1, 0, 1, 0, 1, 0. So your A sublattice is basically the odd, let's say, and A bar is the even lattice points. And then you let it basically evolve, okay? And however, in this case, you are no longer dealing with the non-interacting system. You are looking at an interacting systems because this interact with some local interaction. Okay, and the scale of that local interaction is U. And this is what you see as function of time if you measure the imbalance. If you have delta 0, delta is what I'm calling V here. So basically, if the disorder is 0, the imbalance at long time goes to 0. However, as you crank up the incommensurate scale, you see that the density imbalance goes to a finite value at long times, okay? And then you can do it at different U's, and you get some map in the U over J and delta over J plane, and basically that's the idea. So if you are at 0 interaction, you have extended states at low disorder, localized states at high disorder, and then the idea is as you are turning in on interaction, you basically end up having the localized states for some values, and at very strong disorder, you essentially have the localized states at all values of the interaction. That's from the experiments, okay. So we want to understand this system, understand this dynamics, and see what this long-time imbalance is related to. And for that, well, for the first time in the conference, I guess we are going to hear the K word, which is the Schwinger-Keldysh field theory technique, which is basically a non-equilibrium field theory technique. And just to give you a basic primer, you start with the evolution of the density matrix, and you expand the U and U dagger in some path integrals. So you end up with a field theory which has two sets of fields at each space-time points, plus and minus along this contour. And then you have the matrix element of the density matrix, initial density matrix. Okay, so you end up with some field theoretic structure which has two copies of fields. You can add your sources, calculate your correlation functions in this field theory. So since you have two sets of fields, if I want to write down Green's functions, which is 2-point functions, you will have 4 of them. I don't want you to focus on all the details here. I just want you to focus on this one, that if you write down the 4 Green's functions, there is an identity between them, which just comes from commutation relations. So these 4 objects are not independent, okay? And then to look at it more carefully and take care of this, you work with the symmetrized and anti-symmetrized version of the fields, plus and minus fields. You call them classical and quantum. I'm mostly talking about bosons here. Okay, and then you can again write down 4 Green's functions. One of them has to be 0 now, that's why you went there. And most important, you should think of these 2 objects. There is a retarded Green's function, and the retarded Green's function, you should think of it in the following way. If I give you a retarded Green's function gr xt x prime t prime, it's the conditional amplitude that if the particle was at x prime at time t prime, what is the what is the amplitude that I will find it at x at time t, of course without creating additional excitations in the system. Okay, so that's gr, and then we will have another object which is the Keldysh propagator, which is related to all your observables. So for example, if you look at phi classical star, if you look at the local piece, this is related to the density. If you look at it at I and j, you can relate it to currents and so on. So basically, all one particle observables are going to be obtained from this object. So these are the 2 objects that you need to kind of get yourself familiarized with. Okay. So now what is the okay, so you can say fine, but how do you take care of this fact that you had this density matrix and you had the matrix element of the density matrix sitting in there? And the textbook Keldysh field theory textbooks that we have, a few of them, would tell you that you, well, do one of the 2. Either ignore this term, which means you are only looking at steady states, okay? Or you consider a thermal density matrix, and then this matrix element can be evaluated by going in some imaginary time, okay? So now none of these are going to be useful for the thing that we are going to look at. So we need to find a way to be able to incorporate arbitrary initial conditions in the system. And so the question that you need to ask is, can this matrix element be exponentiated to a lower order polynomial in phi? Because if you can, then you can put it as a part of the action and work your way through. When can this be done? At what additional cost? And how do you calculate correlators in such a theory? Because if you can do that, then, well, I have a way of calculating what I need to calculate for the density imbalance. I'll give you the answer that it can be done for all initial density matrices for both bosons and fermions. And to give you what structure it implies, what happens is you modify your Keldysh action by adding an initial source term. There is a source term u, which couples to a very particular combination, bilinears of the quantum fields. It acts only at t equal to 0. It's a Gaussian coupling. It turns out to be an anti-Hermitian term, couples only at t equal to 0. Okay? So here is the prescription. You first modify the Keldysh action. Then, in addition to u, add the linear sources, take whatever derivatives you need to take with respect to j, calculate the Green's functions or correlation functions in presence of the sources. Okay? Now, there's something that it becomes nice because u couples to the bilinears. There's no cross derivative between u and j. And note that gu does not have any information about the initial conditions here. Finally, the initial conditions are put in place while constructing the physical correlation functions. This is not the physical correlation functions. And that has the structure: you take a g of u, multiply it by a normalization n of u, which you can compute, and then take a set of derivatives and then set u equal to 0. Now, which set of derivatives you are supposed to take will depend on rho naught. So that's how the initial condition gets into your picture. Okay, so maybe we can just look at some simple example. If you have a single mode, let's take a quadratic action. And so I am looking at a rho naught now, which is, let's say, diagonal in the number state Cn, Nn. This is an arbitrary density matrix. This is not a thermal one. And what you get is you look at this matrix element, turns out to be a polynomial of phi star plus phi minus. And of course, then you can exponentiate it by saying that, I can generate all polynomials from an exponential by taking enough derivatives with respect to u. Okay, and then what you do is you take all this derivative taking out of your integrals. That's what gives you this set of derivatives. Remember, it depends on Cn, for example, so it depends on the initial condition. And inside you have this delta Su, which is coupled to bilinears of the fields. Okay? And then if you do your calculation carefully, you will see that the normalization comes because you have a partition function sitting there, which is still a function of u. And that's basically how the structure emerges. This is a sketch of how it emerges. Okay? So 3 steps: add a source at initial times, work out the correlatives in presence of the source, take derivatives, and the set of derivatives depend on you. You can look at this and you can, or you can look at this paper in details. You can do it for all sorts of density matrices for bosons and fermions. I'm not going to go through the details of this, but you have to take my word that it can be done. And if you want to look it up, you can look up in this paper. Okay, so now, of course, this is just a formal prescription. Can you do anything with it? And it turns out that for non-interacting systems, all derivatives can be taken analytically. Okay? So once you can do that, you end up with, this is now I'm writing the physical Green's functions. The retarded Green's function is simply a propagation, and then there are this initial these are the eigenfunctions of the system, psi alpha, psi star alpha j, and then you get a spectrum E alpha. Okay, it's independent of initial conditions, only depends on the Hamiltonian because it's a conditional amplitude. You are not looking at the actual amplitude of propagation in this object. Turns out that you do all of what I had said, you end up with the following answer, that your Keldysh Green's function is at t prime is something which looks at gr at t0, gr star at t prime 0, and then it has to be multiplied by 1 plus 2 nk0. So this actually carries information about the initial conditions, in this case the initial one particle distribution function. Okay, and if you take the time to be same, this has a nice interpretation. For example, ni of t is simply gr of it k0 mod square times nk of 0. So what you are saying is there's an initial distribution function. I am propagating it, and each k is propagated independently. That's basically the sum over k. That's the answer. Okay, so there's some nice physical interpretation of this. So basically, yeah, if it was at time t equal to 0, it's the probability for the particle to be at I at time t, and then you sum over all the nk0's initial distribution. Okay. So now that I have this, I have a way to calculate ni of t. And you remember, if you go back, your MBL and imbalance dynamics required you to calculate the ni of t. Okay? So at least for the non-interacting system, starting from the Fock state, I should be able to calculate the imbalance as a function of time. Okay? So more importantly, if it's a closed system, this is conserved. So sum over I ni of t is the total number. So you get a 1 over n. You get this kind of an object. And this is simply obtained from ni of t. Okay? So in principle, you can diagonalize the system, look at this, and basically get a numerical estimate of imbalance from one particle energies and wave functions. But that's not quite what we are after. I mean, that of course can be done and not a big deal. What we realize is that this object GRIT K0 mod square is the probability of propagating to I if you started at K at time 0. And if you go back and look at Anderson's paper, this is exactly what he was calculating. He was putting a delta function in a disordered system at time equal to 0 and asking how does the wave function spread. Okay? So this object basically can be written as e to the power minus 2 Ri minus Rk over Cl once you average over disorder. This actually defines the original localization length as defined by Anderson. Okay? So with that notation, now what you can do is, okay, this is some geometric sum that you have to do. You can keep on doing that. So the first thing is, okay, irrespective of, once I give you the set A and A bar, now this sum will give you an answer for the infinite time imbalance, and it's just a geometric quantity. So depending this k element of A basically takes care of your initial conditions. Yeah. Yeah. Oh, A and A bar is the initial condition, okay? But the system is disordered. Or if you have Aubry Andre, you put a phase and you integrate over the phase. Okay. So for each disorder realization, we are starting from the same state. That's right. Okay. So what you get is a universal relation between the long time imbalance, the localization length, and some initial pattern. Okay. Now you can put in your favorite pattern and get an answer. So let's look at what the answer is for the thing that experimentalists do, which is 1, 0, 1, 0, 1, 0. And then it just becomes some GP series, you sum it up, and you end up with an answer that the infinite time disorder averaged density imbalance, in this case, is tan hyperbolic A over CL. A is the lattice spacing. Okay? So first of all, there will be a finite imbalance for any localized phase. That's the first thing that you would see from here. And if you are near a localization delocalization transition, CL is large, it goes as 1 over the localization length. So if you want to see the scaling of this quantity near a localization delocalization transition, it would be the same as the scaling of the localization length near the, yes. Yeah. Yeah. Yeah, this will also go as 1 over. Well, no, what I'm saying is that, yeah, I mean, so all I'm saying is the memory of initial state is carried in all of this, and you end up with an answer which is 1 over CL. Yes, it is. Well, no, I mean, the memory is carried because I am summing over k element of A. That's where see, my initial state only cared about A or A bar. Xi does not care about A or A bar, right? In fact, remember, I defined Xi from GR, and I told you that GR is independent of initial conditions. 1, 0. Yeah, I can give you 1, 0, 0, 1, 0, 0. Again, we'll get some. Yeah, it's just a question of summing that GP series. I mean, okay. So that's the first answer. So let's see what happens. Okay, this we written up in this paper. And so let's take the Aubry-Andre model, where as we know that there is a localization delocalization transition exactly at V over J equal to 1. And there's a duality relation which basically tells you that in the localized phase, the inverse localization length will go as log V over J. Okay? That's obtained from some duality relation. So let's see what happens. So what these are, we have basically just diagonalized the system on some large number of lattice sites, calculated mod GR square at large times, and basically just looked at how it goes. So this you can see that if V over J is 0.6, it goes to a constant, there's delocalized. Here you can see, and you can extract a localization length by fitting an exponential here. Okay, you take that and you ask what is the answer if you put tan hyperbolic. This red dots are the answer. Okay, and this guy is basically the dashed line is basically the answer if you put ZL is sorry. This red dots are the answers of I infinity calculated numerically. The black line is the answer if you take the ZL from here and put it in. And this dashed line is the answer if you put in the ZL inverse to be this duality relation. Okay? So it seems to match pretty well. You can do it for the 1D Anderson model, which is always localized. And again, you can basically see that the blue line, which is the analytic answer, versus the red line, which is the numerical answer, matches very well. This is how the localization length goes as a function of the disorder scale. Okay. What about a system with mobility edge? Okay. Now we wanted to stick to 1D, so we went to this generalized Aubry-Andre model, where the Aubry-Andre incommensurate potential is renormalized by 1 minus nu cosine 2 pi alpha I plus phi. Okay, there's a bunch of papers which do this. And this system has a mobility edge. So here is the idea. If you look at that, this is the energy. At low V over J, all the states are delocalized. At large V over J, all states are localized. But you can have in between V, intermediate V over J, where there's a mobility edge going through the band. Okay? And you can actually figure out the value of the mobility edge directly from some duality relation. Okay? So we wanted to ask, suppose we are somewhere here where there is a mobility edge, where there is a mobility edge, what is the answer? What happens to I infinity? And the answer is actually turns out to be simple. So at large times, mod gr square can be written as a sum over states of some objects, okay? And it's of course dominated by delocalized states for large distances. However, if you restrict these states over localized states, because you know where the mobility edge is, you can just look over states which are in the localized region, then of course you will see that this looks like an exponential decay. From this you can define an effective localization length, and you also have a fraction of localized states. And the final answer seems to be the I infinity is simply FL times tan hyperbolic A over CL tilde. And again, this is the numerically calculated answer, and the line is the analytically calculated answer where we fix FL and CL from this object. Okay? This seems to match. So, okay, so what we have now till now shown is everything in a non-interacting system, but we want to do interacting systems. So we add a Hubbard interaction. This is a boson model. We just had a local Hubbard interaction. And interactions would typically, because we are looking at one particle Green's functions, yeah. No, only thing is that you do have a A experiment, and B there is a transition. Otherwise, you have to, in 1D, the random model doesn't have a transition. I think it's just that. Okay, so interactions will lead to self-energies in your Green's functions, and again, you will have a retarded part and a Keldysh part. But rather than go into complications of diagrams, let's understand what these things are in a language which is probably known to a lot more people here. So if you write down, from this, you can write down something called a classical saddle point equation. And if you took this model, added a sigma r and sigma k, and the saddle point equation would have looked like del t minus vi, and this is the Hamiltonian part, basically, okay? Then there is a sigma r, and on the right-hand side, you would get a complex noise term. Okay, so if sigma r is imaginary, this is what would give you dissipation, and the noise correlator you can show is exactly equal to the Keldysh self-energy. So you can either think in self-energy language, or you can say is what I have is if I have a sigma k, I have a noise term, and I have a noise correlator, and if sigma r has imaginary parts, that has a dissipation in the system, okay? So, and in thermal equilibrium, if you reach thermal equilibrium, they would be related by fluctuation dissipation theorem. Okay, so if you want to solve, suppose you know the self-energies in some way, if you want to solve for the Green's function, okay, then you just write down the Dyson equation, okay, there's a non-interacting part, and the Dyson equation for the GK is very interesting. There is a part which looks exactly like what we had in non-interacting system. It's an initial distribution now propagated by the interacting retarded Green's function, okay? Then there is an added part which is related to the stochastic contribution from the bath of excitations that you are creating, because sigma k is sitting here. So what is happening is, as you are propagating, you are scattering, so you are creating excitations, and that's why you decay in the GR, because you cannot come back to the same state after a time. But this bath of excitations that you are creating is feeding back through a stochastic term, through a noise term. That's basically the idea. If you just rewrite this in, just think of it in a little physical way, that's what it will look like. Okay, so now some technical things. It's a closed system. We want to conserve the total particle number, so we need to do what is called a conserving approximation, which basically means the sigmas have to be functions of the full interacting propagator. The only point is that this makes life very hard because you are now looking at integral equations which have to be solved self-consistently. Okay? And then once you have calculated all these, you can again take your formula for I of t and just calculate the, from gk of t, you can calculate the imbalance. Okay? Just one point, usually the first order perturbation theory gives you a Hartree-Fock that does not have a noise term. Okay? And usually the sigma r is also real. Okay? So for example, Weidinger et al. Had also done this Hartree-Fock, self-consistent Hartree-Fock. No dissipation and no noise. So you're not even allowing in your approximation for the system to thermalize. So you are not going to be able to argue whether things thermalize or not by doing a Hartree-Fock approximation because it does not allow a noise and does not allow a dissipation term in your system. So, well, what do? You go to the next order, which does allow, and then walk it through. Let's not look at the details. So this is the answer. So this is at v over j equal to 2.5. So we are in the localized phase. And if you are at u over j equal to 0, you see that the thing just goes and oscillates around some value. If you take gradually increasing u, I guess this is 0.3, 0.5, and 0.7, you see that the decays and decays to a slightly lower value. You can fit this function to an infinite time number plus exponential. These are actually reasonably good exponentials we have checked. And then look at I infinity from that fit. And this is how it was looking. This is the non-interacting answer. And you see that as you go down, increase interaction, it comes down, but remains finite. Okay? Somewhere here you can ask, why are you not tracking the transition? Well, we have a finite size. We can go up to finite times. So all sorts of errors pile up, and I don't think the answers here are quite trustworthy. But what we can show is that you add an interaction to a time, you get a finite number. Now, rather than, okay, so we can of course look at the number, but we can ask what is governing the long time imbalance in this system. Okay? Is there a picture that emerges that tells me what is happening in this system? And for that, as I said, go back and look at what GK is doing. This is one part where I said it's an initial distribution propagated by an interacting GR. However, the interacting Green's function decays in time, okay? And you can see that it will pretty much go on decaying once you give self-energy an imaginary part. That means in the long time limit, this term is 0, basically, okay? So your long-term imbalance is not governed by what was happening in your non-interacting system. It's all coming from this part, okay? So you can do this more, you can look at the numerics and then see that essentially what you get is that I1, which is the first one, goes to 0. It's dominated by the second term. So, but what is happening? What is happening is if you look at the sigma k for the A and A bar lattice, okay, it goes to different constant values. So what is happening is you are creating a bath, but this bath of excitations cannot propagate because it's a localized system, okay? So essentially, the bath remembers, or excitations remember where they were created, which point they were scatterings created them, okay? So all the information about the initial condition is now in the noise correlatives of the bath. And this is what is sustaining the long time imbalance, although there's a decay in the Green's function, okay? So it's effectively you are seeing two different baths for the two different sublattices. Okay, so that's basically what I have for you guys. I should acknowledge my students. Ahana Chakrabarti, who was a PhD student, who has moved to Dresden as a postdoc, and Pranay Gorantla was a master's student who has now gone to Princeton as a graduate student. And these are the two papers. So let me summarize finally what we have. So what we have done is we have extended the Keldysh field theory formalism to describe quantum many-body dynamics starting from arbitrary initial conditions. In this new formalism for non-interacting systems, we obtain a universal relation between long-time density imbalance, localization length, and initial density patterns. Okay, so the long-time imbalance does really tell you whether, at least in non-interacting systems, whether you are localized or not. For experimentally relevant patterns, we have some exact expressions that we can look at in the long-time imbalance. We can also understand this as a function of disorder in the systems with mobility edge, and there we have to look in terms of the effectively localized states. Okay? And this something similar happens. For interacting systems, what is important is that the mechanism of sustaining a long-time imbalance is very different from what happens in a non-interacting system. Both of them give you a finite value, but the way the information about initial condition is stored is now stored in terms of some path of excitations which knows where it was created and what the initial conditions. So I'll leave it here.
So I have a maybe comment, but of course you can then tell what you think about this concerning the interacting part, which is the most non-trivial part of this. I don't have doubts about. So all what you say is nice concerning sort of imbalance, saturation, and initial conditions and all this. So the question or comment is how convincing are your data in showing this? So one comment is concerning Hartree Fock. Yes, so you mentioned that Hartree Fock does not include noise and therefore will not thermalize. So if you run the same calculation with Hartree Fock, you will perfectly see how it sort of apparently shows the kind of the decay of the imbalance. So it therefore the naive idea that since Hartree Fock is kind of single particle, it will always be localized.
The imbalance goes to 0?
Yes.
There is a problem with that. I can discuss with you later. I think I know you're talking about this Weidinger where it goes to some value and then there is some power law decay.
No. Well, so imbalance. So what I'm telling that the qualitatively, if you do this sort of numerics with Hartree Fock only, or adding this next order term, you will see very, very similar behavior in both cases. And in both cases, also in your case, so you say it saturates, but actually it shows also in your plots slow decays. So the question whether it saturates or shows some slow power law behavior is very sort of difficult numerically, since we also know that on the delocalizer side we expect slow power laws, or may expect at least, or may expect a slow behavior. And all these features what you show are in fact very nicely can be fitted, at least numerically, by slow power laws. And as you mentioned, you cannot really, from your data, in order to show that it saturates, you should show clearly that there are two phases. Yeah, that there is a delocalized phase when it decays, and the localized where it saturates. Yeah, then you should be able to define the transition. Yeah.
Okay, sure.
But if you plot the same curves with increasing interaction, you will see there is a continuous behavior. It's very hard to determine a transition, and I think there is a good reason for this, because this is when you do this exactly in the Hartree Fock case, and here you truncate the series, yeah? And so you replace doing real quantum mechanics by solving some classical equations, and I think you, strictly speaking, kill many-body strict many-body localization in this sense. So I think, so I think there is a conceptual problem with, and people in fact tried this. I don't know, you did not cite papers also in this paper that you cited where they did Hartree Fock. They also did beyond Hartree Fock, and there was a they did.
They didn't. Weidinger, I know.
Believe me, they did. So just read this paper. if this is a paper that you cited, this is by Mikhail Knapp and so believe me, they also did beyond Hartree-Fock. Just look at this paper more carefully. And there was earliest paper by Barlev-Reichman, and so it's not so this sort of calculation have been, and people observe it that it's well, basically what I say. So it's not that I doubt that there is a situation of imbalance in the delocalized phase. So so the question is how convincingly can you show with this method this? Because if you could, you could locate the transition in this way, and that's pretty difficult, if possible at all.
Answer, reply to that comment. So first of all, as I showed, I think that part you would agree that the Hartree-Fock does not have a noise term. You don't agree? Okay, you can write down a saddle point that will not show a noise term, that is evident. I can write down the saddle point equation of a Hartree-Fock theory. It does not have a noise term.
So maybe it doesn't have a term that you call a noise term, but physically it does. That's an approximation that certainly will produce, it will produce a noise. Actually, it will produce dephasing, which is stronger than the physical decay.
Dephasing is also there in non-interacting systems. So dephasing is not what you would call noise now.
No. I call dephasing what does not exist in so okay, that's
so then we are talking about different things.
So if you do Hartree-Fock for non-interacting system, it will be exact, and so nothing will delocalize. The moment you will start doing this for interacting system, it will produce you the contributions for typical initial conditions, unless you specifically fine-tune initial conditions to exact solution of self-consistent. Yeah, I mean, of course, self-consistent Hartree-Fock.
So I think, first of all, self-consistent Hartree-Fock does not have a term which does this. What self-consistent Hartree-Fock does have is basically what you are having is U times N essentially as a self-energy, right? And the N, as we have seen, maybe I can show you here, this is, okay, even in the, so let's look at this. Even in the non-interacting case, what you have is you have oscillations, okay? Now, that's in the imbalance. So the two ends are looking at different, basically you are taking a potential, which is now oscillating, because that delta N is changing in time like that. And you add a time-dependent potential and keep it on, the whole thing will go at some point go to infinite heating. And that's
what I'm saying. Just if you run Hartree-Fock for this, you will see essentially the same curves. They will be even more down. Just try this.
No, it's not. I have tried. You think I have not tried Hartree-Fock with this? This is very weird. I'm showing you this data. You think I have not shut down the other term and not tried what
the point is that we also calculated this, so I also know what I do.
Yeah.
So I think we have.
I don't know. You think you remember numbers so that you basically can tell me whether Hartree-Fock curve is above this or below this?
Yes, I think maybe
I should point that out.
You guys can discuss
sure.
coffee, and so I think we are short of time, so we go to the next talk. Let's thank Rajdeep.